So far, I have entered the three values, 45, 47, 49. Then I can enter 51, 44, 48, 42, and 53. So this is the first vector. And the second one is B. That is 44. I have to look at my notes, but my glasses are. So 44, again 44, 49, because I want to use the same data which are in the book, but I don't remember them by heart. So I have to read them. 53, 48, 34, 47, 39, and 51. So, hope I got them right. And if you find some differences with those in the book, and doesn't matter. What are these vectors? So, they represent, at least I intend them to represent, the result of chemical analysis relating to the content in oil of sunflower. So I took 1, 2, 3, 4, 5, 6, 7, 8, 9 samples, sunflower samples, and measured the oil content with two different methods. So A is the first method, and B is the second method. And of course, the first value in A matches the first value in B, meaning these are two measurements taken in the same sample. So they are matched by position. First sample, second sample, and of course, otherwise it doesn't work. So this is important. Now, we might wonder, is there any relationship between A and B? I mean, do I get the same results by using the two methods, or do I get different results? Okay, so when we have quantitative variables, we could plot simply them. For example, here I can plot, I use the function plot. I can plot B as a function of A. All right. So you should obtain something like this. Of course, we can make this plot a little bit more pleasing to our eyes, but that doesn't matter at the moment because we are just studying the relationship between two variables, and we can see that when A increases, B increases as well. But they do not increase following a straight line. So it is a measure of there is a relationship of joint variability. Okay, so this kind of relationship between quantitative variables is usually called correlation. Okay, so we can have positive correlation when one variable increases and the other variable increases as well. That would be a positive correlation. That's the same as we see here. Okay, so that's positive correlation. Or we could have negative correlation. That means that one variable increases and the other one decreases. That would be negative. Okay, so I would have a sort of a relationship going down. This goes up, in the other case it goes down. Then I could have the case of no correlation. That means that one variable changes, increases or decreases, and the other one is unaffected. So meaning there is no relationship between the two variables. So correlation can be either positive that means that A increases, B increases, or it could be negative. That means A increases, B decreases, or the other way around, of course. And then we can have no joint variability, no correlation. That means A increases, B no change, or the other way around, of course. So how do we measure the correlation? We have one statistical indicator which is very useful, and it is the so-called Pearson correlation coefficient. Pearson was a famous scientist living in the UK at the end of the 19th century and at the beginning of the 20th century. He was very famous, actually, and he invented this correlation coefficient, which takes values, between -1 and 1, right? So if we have -1 is perfect negative correlation, right? So 1 would be perfect positive correlation. When I say perfect, I mean that the graph is a straight line and all the dots are in line, right? So the second variable changes according to the first one by the same amount. So it's a straight line. That's perfect correlation. Of course, the correlation can be less than perfect, like the one we see now. So the value of the Pearson correlation coefficient would be lower than 1 or higher than -1. If we have 0, 0 is no correlation. Right? So it doesn't matter. In the book, you will find the formula to calculate the correlation coefficient by hand. You might take a look at that, but we will never calculate the correlation coefficient by hand. That's not really. We used to do that maybe 30 years ago when we did not have the computers. But now it's really silly to make a hand calculation. So we use the R function. That is core, the function core, and I'll pass the two vectors as arguments. So core A and B. And we see that the correlation is positive. And we see that the result is 0.919. So which means that the correlation is positive, and we saw that already because A increases and B increases, but it is not perfect, it's lower than perfect, but it is close to 1. So it is a good correlation. In some cases, it is low, even lower. When it approaches 0.1 or 0.2 or 0.3, then we say, okay, the correlation, if any, is very small. In this case, it is good. So that's all. I mean, the correlation is perhaps the most important relationship between variables, and we have to know that. We at least have to know what the correlation coefficient is, what the values it can assume, what values it can assume. We should know what does -1 means, 1 means, 0 means, and whatever. So any questions about the correlation coefficient? Yeah. Now I will go ahead for a while. If you don't have questions here, no questions here, no questions at home, that's good. I mean, I like questions, so you have to ask questions when you have, but if you don't have them, of course, you can't ask them. So I want to talk about two categoric variables. What shall we do with two categoric variables? We cannot calculate the correlation coefficient, of course. I will use another data set that is called data hair eye color. So we need to be careful here. Look at the data set and the name. The H is capital, the E is capital, and the C is capital. You see that's a camel notation because the case changes when the word changes. And look at color, it is written color without the U. So American spelling, not English. That is a database about the color of hair and the color of eyes. I mean, there might be a relationship between these two variables because we know that by heart that people with black hair more frequently have black eyes, and it's less frequent to have a person with black hair and blue eyes. So that's this is the result of a survey about this fact. We have, you see, if I go in hair, eye color and look at the data set, we find that this data set is composed by two tables. So this would be an array with three indices, right? Because we have one index for the columns. First of all, the rows. So one index for the rows, one index for the columns, and a third index for the table, male and female. So we now have to work with, let's work with female. So I have to index. I want to create a tab, an object called tab, taking second table of the hair, eye, color dataset. So it's like this. You remember the indexing. So I have three indices here. So I want to take all rows, all columns for the second table. So the one about female. I'm more interested about knowing the hair and eye color of female at the moment, right? So this is my table. I give you a few seconds to get the table. And I drink. So that is the point you should have come to. Did you manage? Okay. Did you get to this point? No. So I have to change check what's happening here. And I'd like to have a short feedback from you at home to understand whether you managed to get to that table. Yeah. Yes. Okay. You. Let's run from line 21, please. One line after the other. No, I run? Yeah. No, not even need to select. Just put your cursor on the line like this. Yeah, you need to select. Remove selection. And you, okay, from there it's okay. So go with Control Enter. You press Control Enter. Put it together. Okay, fine. One, then again, you see as it goes ahead, so Control Enter again. So you don't need to press here. Control Enter again. Control Enter. Then Control Enter again. Okay. You miss one value here. Okay. Yeah, because you have 8 values in A and 9 values in B. Thank you. So, Valeria was okay. What about the other ones? So here, Claudia is okay. Kang was not okay, but we found a mistake. The other ones are missing. So, do you have any particular problem with accessing this table? So I will tell you, I do not get any feedback, so I'm not sure whether I have to worry or not. I go ahead. What we did was to open a data set, and we discovered that that data set was indeed composed by 2 tables. Each table has rows and columns. So we created a variable tab containing the second table for that data set. So that was the table about female. And what's this table? This table represents the frequencies, the absolute frequencies of subjects in each class. And the class is composed by the combination of her classes and I classes. So for example, we have 36 female with brown eyes and black hair. And we have 66 female with brown eyes and brown hair. So more frequent. Then we had 16 female with brown eyes and red hair. And you see that brown and blonde is very infrequent. And the mode is brown and brown because we have the highest absolute frequencies. Right? So this is called contingency table. Contingency table. So the contingency table is a table of contingencies. I mean, frequencies for two classes, two groups of classes, two variables. So this is a way of summarizing count data for two variables. Now we can wonder whether we have dependency relationship. What is a dependency relationship? In this case, a dependency relationship is a relationship where having brown eyes, for example, is not independent from the color of the hair. So, I mean, if you have the hair of some color, that implies that you more likely have the eyes of a specific color. So the two traits are not independent. Two traits are independent when the probability of having hair of some color does not imply anything about the color of your eyes. That would be independent. And in this case, we see that it is not independent, clearly, because we have some combinations which are more frequent than others. So we can suppose that there is a dependency relationship between the color of the eyes and the color of the hair. So we can measure the dependency between nominal variables, and we use an indicator which is called chi-square. Chi-square. You have perhaps heard about that. Also for this indicator, I put the formula in the book because it's useful to go through that. We will not do this now because I think it's impossible to illustrate a formula in these conditions. I mean, talking to people over the network and having people here, I should use the blackboard, and it's almost impossible, but it doesn't matter. I just like you to know what a chi-square is. The chi-square measures the relationship of dependency within a contingency table. Okay, so if the chi-square goes from 0 to a maximum value, chi-square max, which is the product between n is the number of individuals, and n by number of rows, columns, whatever is the lowest. Okay. So, number of rows of columns. So I have to take the lowest value between the number of rows and the number of columns. So, how do I calculate such a chi-square value? I calculate the chi-square values very simply. I simply have to use the summary argument. However, if I use the summary method, I do not get the correct. Yeah, well, these are correct. Yes, because this is already a table. Because if you want to obtain the chi-square value, then you have to use as an argument a contingency table. So you cannot use a matrix or a data frame. In this case, tab is already a contingency table, or at least R was able to understand that it was a contingency table. Otherwise, you should use a syntax like this. So you have to tell R that this is a contingency table. This would be the more complete comment. and it gives the same results. So we see that the chi-square value is 106. And you know that this goes from a minimum 0 to a maximum of 313 cases. The number of rows is 4. The number of columns is 4. So we can select 4 and multiply it by 313. So the maximum would be something like more than 1,000. And we have 100. So we have a certain degree of dependency. Not high, but a certain degree of independence. So that is what I wanted to tell you. So we have two kinds of relationship: correlation, which is useful to see whether there is a relationship between quantitative variables, in the sense that one increases and the other one increases or decreases. And we have the dependency relationship, which is typical of categoric variables, nominal variables. And it means that having one particular class in one variable implies that we are more likely to have a particular class in the other variable. And in this case, we use the chi-square index, which goes from 0 to a high number. And it is important to see where we are, whether we are close to 0 or whether we are close to the maximum. In this case, there is a certain relationship. We will say that this is significant, but we will talk about this later. We have a certain relationship of dependency. Ciao, Valeria. Okay. That's not really high, but it's enough to say that the color of ice is dependent or associated to the color of hair to a certain degree.